um, step number one is to especially when you have frictionless thing, energy conservation. See how far that takes you, right? I mean, it really, a lot of problems get done just by that. All right, then uh, then kind of hit upon the momentum conservation. All right, momentum, angular momentum conservation. That's really like, this is like almost 60-70% the problem that you're going to encounter is going to be these two steps. But sometimes you have to keep in mind that uh, there are mm, there are like you get stuck, and then you're going to try. Finally, you have to work out the force. So it's going to be F equals to dp dt, or a simpler one. You'll do it. Okay, F equals to ma. If you know what the a looks like, then it's really, this may be, if you know what the a direction looks like, etc., and what the magnitude might look like, that is one of the give that it's an F equals ma problem. But here it's not very clear, so we're going to start with the energy conservation. Okay, so the problem is this, maybe you read the problem already, so let's read together. So you have a frictionless, this whole thing is frictionless, and we just cut out, it will be a circle, and this is fixed. So if the ball could roll, I mean, I was stuck in that. If this guy is going to go this way, the ball is going to go. That was my main problem, and I kind of didn't even. It wasn't kind of. It wasn't explained in the problem, and once we realized ball is supposed to be fixed, then our problem became really easy. Okay, at that point it was just a matter of walking through these steps. All right, so let's look at this. This comes down here, at some point it's going to fly off. Okay, so it's going over here, it's going with some speed v. We don't know what speed that is, but we know from here to here you have lost potential energy, and it's supposed to be v equal to 0 over here. Now if you're like exactly at top, exactly up above, it will not go anywhere. So it has to be placed just infinitesimally to the right or to the left. Okay, so that's kind of assumed in this problem. Although if you write all of those things in a problem statement, you're going to make the problem statement very long, and sometimes things are left out and you have to interpret the problem, and that's really part of the reason physics is hard, because the problems require so much specification that a lot of this is just left out, and you have to kind of guess what the most reasonable thing is in this situation. And the most reasonable thing in this situation is, of course, if you leave it right at the very top, the center of mass of the block is right above it, the symmetry line, one of the symmetry axis of the spherical ball, it's going to sit there. There's nothing to move it. We're not talking quantum, which it fluctuates and then it's going to move, right? We're talking about classical, so it's just right there. Okay, so so we know v is 0 and it's over here, and it has gone this much. So we have to figure out this delta H, and it's lost this much potential energy, again kinetic energy. So this is I and this is F. So kinetic energy is gained half mv squared, the v minus 0. This is a change in kinetic energy. It must equal to change in potential energy. and this will be written as a positive thing. Make sure that this, because this is positive, so this better be positive. Okay, so how much did it drop? Well, the radius of this usually given in this problem. Okay, I forgot to give you the radiuses r. So if you look at this big thing is r, and this will be because it went out here, and we want to know what that angle is, so we assume it's theta. So this part will be r cosine theta. So it lost r minus r cosine theta. So mg r minus r cosine theta. Of course, cosine theta is less than 1, so you don't need these guys, and this is just fine. This is mg r 1 minus cosine theta. So we don't know theta, so that's the one we're supposed to figure out, and we don't know this. If so, this is not enough, right? You can figure out theta from here. So like, okay, so 1 minus cosine theta is equal to mv square over 2 mgr, and m got cancelled out, so etc. If you know v for sure, then you could solve it like this if there was some numerical value. I'm not going to go do more of this, because so we'll just treat it as one equation I know in two variables. Okay, so this is not yet, is not going to be helpful, because we have two variables and two unknowns and one equation. So we know m got cancelled out, so we didn't need to know m. So we know g, and this is given, so those are given. Okay, so given g r. Okay, so now momentum is not going to do any good here right away. There's no collision and no, so it's not a rocket problem, etc. So we are not going to be helped by momentum consideration. So we skip over the momentum consideration. So we have to go F. And clearly, if the V is that way, then at this point, it's still just look a moment before, okay? So before it flew off. So we just look at a moment t minus dt, okay? So it flew up at t, but I'm going to look at a moment before that. That is critical, okay? So a moment before that, it's still going to be very close to v, okay? And it's going in a circle. And so if you look at it, it's going to be a force will be mg, and there will be a normal force which will be in the same direction like that. The normal force will be pushing it out at this moment, and combination of these two is acceleration. Centripetal acceleration is like that, and then there is an acceleration in that direction. That's why it was speeding up, okay? So there is a tangential acceleration and there is a centripetal acceleration. So centripetal acceleration is v square over r, okay? Then you can write if it's mg, this is theta, this theta. So along the radial direction, along this direction, so radial direction, the equation look like mg cos theta, that way, this guy's component, and normal will be going normal. The normal varies with theta. For instance, over here, normal is almost same as mg because there's no acceleration here, because v is 0, and so but over here it's different. So n depends on where I am. So just I'm going to put n sub theta. So I am at theta place, and that should be equal to, we're looking at this direction, and that's the acceleration, mass times v square over r. So I've got another equation, but I've got this n. So if you look at what happens, now I wrote the equation for t minus dt. Now let's look at equation at t plus dt. T plus dt. What will happen in t plus dt? You know, the normal is, it's not touching anymore, so there's no normal. And this and t, this time t in between there, all of these are just infinitely away from each other. So the situation is all same. So you'll say this is the moment, this happens at t, so this is the moment when n is actually 0. There is, I know there's a moment later, it's really obviously 0 because it's not touching, but that at moment t, it may still be touching, right? But we're going to say that t will be, for us, is going to be this t plus dt. As close to t as like, but a little bit when it's not touching. So this is 0, and then now we have really everything known here, except v and theta. So we have two equations of v and theta. So over here, we don't need to know v, but some question may ask v. M got cancelled out, and so this one says v square. I don't need to know v, I just need to know v square to solve for theta. So v square is g times r cosine theta, and this guy is saying v square is 2 times g r 1 minus cosine theta. So these two of them are the same point in time, at time t. Both of these true at time t. So the right side is 0. The right side must be same as the left side. So okay, so equating them, so 2 times 1 minus cosine theta equals to cosine theta, and so 2 equals to 3 cosine theta. Bring these 2 on the other side, the 3 cosine theta. That means cosine theta equals to 2/3. Okay, it came out to be less than 1. That if I had gotten 3/2 or something like that, I would worry, because cosine can be only between -1 and 1, and within the 90 degrees it's going to be all 0 and 1. So the answer for theta is r cosine 2/3. Okay, that's the answer. So you can look it up in calculator how many degrees it is, but I will not do that. So suppose the question was also find v square. So v square or v, so v will be speed, it will be square root, because I'm a speed, gr cosine theta. So it's going to be square root of 2/3 gr. Okay, it was a good problem. I just a request from you that if you have subscribed, oh great, I appreciate that. If you haven't subscribed, please subscribe to this channel. It helps distribute this conceptual discussion that we're having, and also a lot more people can know about it. Another thing you can do is tell your friends that you found this channel. If you found it useful, definitely spread the word, and you can tell your teachers and so on. Okay, so with that I will stop, and I will see you in another video. Bye.